Okay, let's start with this descriptive or phenomenological explanation of absorption of light by matter. Now you're going to see me break down some other phenomenon as we go on, again, between sort of phenomenological or descriptive explanations and mechanistic. And here's the first example. And in this example, imagine that we've got a piece of matter of some kind, right? For the moment, it doesn't really matter what it is, just that we have some, right? And let's say we have incident on this bit of matter here. We've got a light beam coming in, and we're going to write down the incident light beam intensity as I sub 0, right? And we're going to have a transmitted beam of light that comes out of this as well, right? And it's going to have a output, right? We're going to, again, I. And our bit of matter that we're looking at here is going to be of a particular dimension. We're going to give it dimension sort of L, all right? Okay, so we're going to be considering then the intensity of the transmitted light as a function of the amount of material that our light transmits through. Okay, so the way we want to start thinking about this is sort of breaking this down, right? We want to come up with a quantitative description of this process, right? Even though it's fundamentally phenomenological, we still want a quantitative description. We want to be able to predict based on some properties of the matter, its dimensions, other things, I'll get back to that in a minute, predict the amount of light that's going to be coming out, right? Or use the amount of light that's coming out to learn something about the material that the light was transmitted through. All right, well, to do that, let's break this down. Let's imagine we've got in here the light passes through, say, some differential volume, some small bit of the matter here, right? So it comes out here, right? So if we sort of think about this thin, we're going to consider this like a differentially thin slice of the material in here, right? So that we can describe that as the width of that as being different, some differential bit of the length, right? Okay. So how do we derive an expression that lets us predict or understand how much the light comes out given some other set of properties we know about the system? All right, well, we can begin to write something down here. We can say, well, if I've got a differential volume that the light went through, I can imagine, say, a differential change in the light intensity, right? So it's okay, I can write that down. So that would mean may the light, and I can normalize that to the amount of light I put in, right? So I could say, well, the amount of light that came out, the differential amount of change, right? Of the light that came out, I can write down as like, well, d sub I divided by I, right? So I is the amount of light on the incident side here, and d sub I is the amount that came out on the transmitted side, right? So that would describe the change in the light intensity from one side of my little differential slice to the other, right? And I gave it a minus sign just by convention, because the decrease in the intensity by convention gets a minus sign in this expression. Okay, well that's kind of cool. What's that proportional to? What would that minus di over I, what would that be proportional to, right? Well, it seems like it's going to have to be proportional to a couple of things, right? It's got to be proportional to certainly my differential volume, however big that happened to be, right? It's got to be proportional to something else about the material, like how absorby is it? How well does it absorb the light, right? Now, if you're talking about a solid, you'd be thinking about density and whatnot, but we're mostly going to be thinking about things in solution, right? Because most of biochemistry takes place in solution, not in solids. So we're going to think about the amount of material there as being related to the concentration. So the differential change in the light from one side to the other of my differential slice, the amount that it changes has to be proportional to the amount of matter that's in the slice, which in this case will be proportional to the concentration. I'm gonna give that a C, right? Okay, okay, that's cool. Now, like we've done before, we need to do something to make that proportionality into an equality, right? So I can just write that again, D sub I divided by I. We wanna turn this into an equality. We know it's gonna be proportional to the width of my differential volume. We know it's gotta be proportional to the amount of the matter that's there. And the proportionality constant we're looking for is basically how well does any bit of that matter absorb, right? How absorbing is it? Is it transparent or is it really dark, right? That gets a name, that proportionality constant, right? And it gets a symbol. In this case, I'm going to use this lowercase epsilon with a prime, right? And adding that proportionality constant, which is known, as some of you may remember, as the extinction coefficient, right? Times the concentration times my differential change in volume, right? Cool. All right. Another thing you note, right? Are there any units on the left side of that equality? D sub I over I. Now, whatever units I'm going to use for intensity, radiant power, candles, whatever, watts, whatever you felt like, it's going to cancel out, which means that's got to be unitless. All right, what are my units on the right? Differential volume, length. Okay, that's going to be some measure of length, inches, right? Centimeters, something. Concentration. Okay, that's going to probably be molar. And to make this unitless, my extinction coefficient has to be in units, and just use the standard convention of inverse molar, inverse centimeters, right? That's the standard convention for extinction coefficients. It doesn't have to be, you can change that, but the standard you'll generally see is extinction coefficients have units of per molar per centimeter. Okay, well this is cool, right? Because I now have a fairly simple little ordinary differential equation to work with, right? Because what I want to do, remember, is I want a function that gives me predictions, right? If I know one thing, I can predict something else. So I need to solve that simple little ordinary differential equation, right? And that's pretty simple, right? Variables are already separated, so it's not so hard. So all I have to do is integrate it, right? So I can move that minus outside the integral, integrate from an intensity of I to I0, and now making this look a little more like 1 over I di, right? Which is now equal to my epsilon prime times C. Remember, those are constants, right? They're not variables. And then I just need to integrate from 0 to the full length dl, right? L dl. Pretty cool, right? Pretty simple. You guys may remember that integral, definite integral for that 1 over a variable, right? That's easy. That's just a logarithm, right? And then you run the limits, and you end up with integrated expression that is simply this, where the natural log of I0, the incident radiation intensity, divided by whatever comes out the other side, is simply equal to the extinction coefficient times the concentration times the length of the cell. That's pretty freaking cool, right? That means a couple of things, right? If I knew all three of these parameters over here on this side of the equation, I could predict that ratio. Right? I could predict how much light would come out. Right? That's true, but where this really shines is if I take that ratio, I measure it experimentally in a spectrophotometer. And if I know that value, if I know also then the extinction coefficient, and I know the length of my measurement cell, I can get the concentration, right? That's the great utility of this particular equation, right? And it's often written in a different form, right? The typical way this will be written is using something known as absorbance or optical density. And you've basically just seen the definition of it. So absorbance usually gets the symbol A. As I said, it's also known as the optical density. And you may sometimes see this written as OD, right? Is simply the following. A, the absorbance equals log of that same ratio, I0 over I, right? Which equals epsilon CL, right? Now notice a couple of things, right? Two or three things here. First, that's a really important equation. You should remember it, all right? You should remember, along with the Gibbs equation, the relationship between the equilibrium constant and free energy, and a few others. This is one you need to commit to memory. This is known, of course, as the Beer-Lambert law. And it describes this quantitative relationship between absorption and concentration that is so fantastically useful for doing chemistry and biochemistry, right? All right. Now, a couple other things. One, notice that I switched from natural log to log base 10. Okay, that's just the standard convention. That's for a similar reason like we did with the Henderson-Hasselbalch equation. You know, you're working with log base 10. It makes working with integer numbers easier to think about, right? But what that sort of has a bit of a consequence, which is that the extinction coefficient I'm now using is related to that extinction coefficient we started the derivation with by a factor of 2.3. Specifically, the extinction coefficient, the standard extinction coefficient, is just equal to the one I started with, right, divided by 2.303, right? Okay, doesn't matter for most purposes, but you know, given the little derivation I was going through, for completeness, it's worth remembering that. Okay, so again, the amazing thing about this relationship, or the incredibly useful thing about this relationship, I go into an instrument that accurately measures the amount of light absorbed in a cell of a known size. I have some material in that cell, and I happen to know the extinction coefficient because I've measured it some other way, or I know something about it for some other reason, right? And I know the length of my cell because I can measure it, and standard cells are often going to be, for basic absorption spectroscopy, a centimeter is fairly common. If I know those things, I can measure this. I know these guys here and here. I can accurately with precision, measure the concentration, right? Okay, so it's the reason that absorption spectroscopy is such an incredibly useful thing, right? Something that you want to remember this relationship for is because of the great utility of being able to measure concentrations by just measuring absorption. Now, one other thing to sort of think about, right, worth noting, most modern spectrometers can measure optical densities or absorptions, right, in a range of somewhere about, they've gotten better than they used to be. They can now measure somewhere around 0.01 to about 2 in terms of the absorption, is where the general rule of thumb would be. And some spectrophotometers, not even that much. Older ones, right? Older ones, or maybe not as high quality ones, you might only trust those to between, say, 0.1 to 1, depending on the spectrophotometer, right? Here's something to think about, and we can talk about this in class. Why? Why would a spectrophotometer, maybe a really good one, maybe only be good to an absorption of 2, or only be good to an absorption of 0.01? Think about that, and we'll talk about it.